share my screen. Okay, cool. So can everybody see my screen and hear my voice? Okay, cool. So yeah, perfect. So yesterday we covered synchronized and race condition, right? And for yesterday's race condition, we used the synchronized to resolve this problem. But actually, there is still another way to um, resolve this problem. So let me first copy paste what is race condition. So the reason why the race condition happened is that two threads try to update our value at the same time, right? So yesterday we used synchronized to make the increment method to be critical in order to make sure that at the same time only one thread can update our value. So keep in mind is that if we can like satisfy this requirements, then we can still like achieve the thread safe, right? So the key here is to make sure that at the same time, only one thread can update our value. So besides using the synchronize, we can further introduce one instruction called CAS, that is the compare and set. So what does compare and set do is the compare part and the set part happens in one instruction. So that is secured in the hardware layer. And what does compare mean is that when it tries to update our value, it will first check whether the value is the expected value or not. Rather than it will not set the value, it will not update the value. And so you see, if we are trying to update the value according to the old value, right? So if the compare and set happens in two steps, so even we can make sure that every time there is only one thread trying to update our value, we can still not make sure that our update is accurate. That is because suppose this two thread read the old value like 101, and when if the compare and set happens in two instruction, then both of them when they compare the current value with the expected value, that is the previously read value. So the previously reading value will be the expected value, right? And when it try to compare it, both of them will find that the expect, because currently only these two threads are trying to update the value. So now no other threads updating it. So two of the threads after comparing it will both find that the current value is equals to the expected that the previous read 101 value. And after that, both of them will start to set the 101, like plus one to it and set it to 102. So it's not thread safe if the compare and set happens in two instruction. So there is there is like a hardware implementation to make sure that the compare and set happens in one instruction. Um, instruction. Okay, so this is called atomic. So this is an atomic instruction. Make sure that keep in mind that these two steps happens in one instruction. So it will be more like you are turning on a switch. So you only turn on the switch when the switch is off. So the compare is like you are trying to check whether the switch is off, and if it is off, then you like turn it on. So the same thing happened in here. Both of the thread will first read and value and make it to be the expected value. And after that, it will try when it try to update it. So if it not check, like have any check to update, then there is a risk that both of them will update it to 102, right? So after when it perform the updating, it will also perform the compare. So only it will only successfully update the value into 102 when the current value is equals to the expected value that it previously read. So in this way, it makes sure that if once, and also in the hardware layer, it makes sure that at the same time, only one instruction can happen. So in this case, if the thread one successfully like executed the CAS operation, then the value will be updated to 102, right? And also make sure that we are using compare and set to update the value. So when thread 2 trying to execute the CAS, it will find that the current value is 102 and not equal to the expected value 101. So it will fail and it will read the value again. So now it will failed updating. So it will read again. So read the new value like 102 as its expected value. And then it will try to start the CAS again to compare the current value with the expected reading value 102. So if the expected value is equals to the current value, the CAS will successfully update the value into a new value like 103. So this is what CAS do. So CAS like make sure that you only sorry, let me mute him. So CAS make sure that you only update the value when the value is equals to the value that you are expecting. So if the value is not like in this place, in this case, if the value, when you're trying to update, the value is not expected to the value that you are, if the current value is not to the value that you expected, then that means this value has already been changed. So you have to fail your CAS and read a new expected value and try to do the CAS again. So this compare, make sure this with this compare and set, it makes sure that when you update your value, you have a check. And also this CS in the hardware layer, it makes sure that at the same time, only one CS operation is performed. So in this case, we can also like uh, make sure the updating is thread safe, right? We are making sure it's similar to the synchronize that we make sure at the same time only one thread is updating our value, and also we're only updating the value when the value is um, equals to our expected value. So um, this compare step is like kind of also is very important. So uh, is like if when you're updating, if you not check whether the current value has changed, like is not equals to your expected value in, and you update it, even though in the hardware layer, it makes sure that only like at one time only one instruction can happen. It still can be not thread safe, right? If you're not up when you update, you do this instruction can at the same time can only happen once. We when we update, we do not check. So if we do not, let's say if we do not compare, we just set, something will happen like this. So even though we make sure that at the same time only one instruction happened, but it the T1 and T2 first they both read the old expected value as 101, and T1 will start updating, and at the same time T2 cannot updating, but uh, if the T2 updating the value without comparing it, then it will just according to the old value to update it still be 102, right? So this compare is also important, and also this compare and set must happen in one instruction, just as I explained previously. If not, it's still not thread safe. This compare and set is atomic instruction happen in one step, and so both of them are like very important. So this is the idea of CAS. Like if you have, for example, if you have a something method called compare and set, you will first take your like the value that you want to update it, and also you will need like a expected value, and this one is the expected value that you are previously read, and the third input parameters will be the new value that you are trying to update to. So the meaning of this method is just like the idea we explained previously, that when you trying to update it, you first check whether the current value still equals to this v, that is the expected value. Only when the value is equals to the expected value that you read, you update it to the new value. So uh, and this will be just like the yesterday, the variable we're trying to increment, it will be the variable name, like specify which variable that you're trying to update. So any questions to this idea, like the CAS? If is the method already been thread safe or no. So CAS, as I said previously, this is like every machine will have its hardware implementation. So it will provide you a hardware instruction implement this CAS operation. So you do not have to. How do we activate it? So you do not have to like activate it, just like a method that provides to you. Whenever you use this method, like there is a class called unsafe class. So it will provide you a lot of compare and set method. You can directly use it. Like you just if you want to like use compare and set to update this your value I, your like attributes I, then you just use the compare and set method from the unsafe class. So no need to like something to activate or like that. Just a instruction that they already provide to you. But like for the idea, does everyone like comfortable with this idea? So how we make sure that using CAS, we can also like achieve the thread safe. If everybody like good is comfortable with this idea, we can further check some Java collection implementations that using this CAS to keep thread safe. But actually, in the real world project, like those Java collections, just the CAS is not sufficient, because you see, there is a compare step, right? So that means we must always have the access to the most up-to-date value. Otherwise, when we compare the expected value that we previously read with the current value, if we even do not have the access to the most up-to-date current value, then the compare is meaningless, right? So basically when we have this compare and set instruction, when we try to do some thread safe updating, we also need the keywords volatile, right? So we have to make this I to be volatile. So every time when we try to compare this previously read expected value, we can make sure that we are comparing it with the most up-to-date value. And only when the expected value equals to the most up-to-date value, we update it to the new value. And always keep in mind that this instruction is atomic. That means this two-step compare and set happens in one instruction. It's not happens in two steps. It's like a switching a switch. You are only like turn on the switch when the switch is off, or and only turn off the switch when the switch is on. So the first step, so it's like a condition setting. So you only set the value into into a new value when it satisfies the condition. So this is the magic of like the mechanism of compare and set. So basically, we will use volatile plus CS to achieve the thread safe. And actually, the real compare and set has the idea is same, but the implementation is a little different. So if you got this idea, you can just keep this idea in mind. But the implementation is that it not directly like specify which attributes it's trying to update, but it's like suppose you have a class, maybe just randomly name it. So and you have attributes in it, maybe integer I, and when we try to update this value, how we specify that this value, this attributes, this data member is the data member that we're trying to update is that we will first provide, like suppose we already created like we have a instance from this class, right? And what we're going to do is we will first specify that which object this attribute is belongs to. So the first parameter will be the object that contains the data member that we are trying to update. And later, the second value will be the offset of the data member. So it's like we will use these two together to find the data member that we are trying to compare and set. So the offset is something you can think in that way that you have a array, right? And this is like the head address of the array, and you can use the offset to compute a specific element at a specific index, right? So you can use both object and offset from this object to access the data member that you are trying to update. But the idea will be the same. Still, these two attributes just function like the previously I write in here. Just in here, we just use these two parameters to specify which data member we are trying to compare and set. And the rest of the two parameters will be the same. Like one is the expected value that we read previously, and this is the new value that we are trying to update to. Like in this case, we just want to increment by 1, so just v plus 1. So this is the idea for compare and set. So any questions related to this idea? So let's just make sure that this idea is clear. Then we can check a library called Atomic Library. It provides a lot of like integer or Boolean value that atomic integer or atomic Boolean value that are thread safe to increment, because eternally it using volatile plus CAS to. Could you give a simple demo about how to implement it? Because the I will show you the source code, like how those atomic integer are using the volatile and CAS to update the data member inside it and also make sure it's thread safe. But because the unsafe method need to use the reflection to instantiate it, and also like the code is kind of tedious, but the idea is this is simple, but we can try to see the maybe let me atomic test. So we can have, if I recall correctly, called atomic integer. So we can call it AI, maybe just atomic integer. So let's try to see how the compare volatile and as long as the compare and set is using. So keep in mind that we will use compare and set to with volatile to thread safely updating a variable, right? So this atomic integer class will have a eternally it will contains a data member that we are trying to update it. So here you see this is the value that we will use compare and set to update it to make sure that this value is thread safely updating. So first, as I mentioned before, it has to be volatile. So the volatile means when we try to use compare and set, we can always compare the expected value with the most up-to-date current value, right? And here, this value is the offset of our lowercase value. So this is the data member we are trying to update. And this is the offset of this attribute. So you see, this is a reflection method that you can get the offset of this data field from the object. So you see, you provide the class and also you provide the field name, and then this method using reflection, it will return the offset to you. That is, you can imagine it as the like the offset of the array, but just the idea is kind of similar. Like you can use the offset to access this data member when you got the object, right? It's like the idea is like when you have the um, address of the array, then you can use the offset to access the target element. So it's same when you have the object, you can use the offset to access the data member from this class, from this object. Or so and also now we will try to update this value thread safely, right? And let's see the method. You see, there is a comparison set, and they have an expected value and new value. But let me directly go to this method. So you see, this method called get and increment. So the get means it will return some value, and because the get is before the increment, so it just returning the previous value. But this doesn't matter. We not care what value we get for now. Let's just focus on how it thread safely increment the value field. So you see in here. So this means the object invoke this method, right? So we will create an atomic integer class type object, and this object will give it here. And this value, remember we explained previously, the offset, right? So combining these two parameters, we can specify which field we are trying to update, just as I explained previously. And this delta is the value that we trying to increment. Uh, so we are trying to increment by 1, right? So here, this method just every time increment our value by 1. So let's why use offset instead of this value? I think this is I'm also not sure about this, but the Java just implement in this way, maybe due to some design reason. But I'm also not sure the reason, like why they just use the this value to directly update it, but using the reflection. I think maybe it's more safe, or if we just use this store value, maybe some error will happen. But I'm not 100% sure. Because you see the this store value will just be a address, right? Because it is like a reference variable. But using the using this way, so we are using a address value compare with the address value of the object compare with the offset. I think maybe it's due to some null pointer exception to avoid some null pointer exception or something like that. I'm not sure, but so reflection reflection is like when you learn like Spring LC or the same idea like the inversion of control or something like that, they will use a lot of reflection. Like for example, the method we used previously, like the class for name, it is a reflection. Like it using the class name to return the class itself. And also here you see this reflection mechanism is like using the name out field to return the offset of it. But for the definition of reflection, I'm also not sure about that because I haven't read that. It's been a while that I read the reflection, but the idea is like, for example, also like if you have a method inside the object, instead of um, directly calling this method, you can use reflection to call this method. Like you can access the method from the just similar like this. You can provide the method name and the object, and then it will return the like the uh, but you can have access to that method. So, like sometimes we have the private method, right? We cannot directly invoke this private method outside from the class, but with the reflection, we can do that. Actually, we can set like the access parameter to be true, and then like using the reflection method to even the private method outside from the class that defined it. But maybe in the future lecture, like the lecture that conducted by my supervisor, he will introduce detailedly for the examples for reflection. Yeah, but I'm also not very like expert on the reflection. So yeah, but, let me resume what I said previously. Yeah, here. So the get and add int. So this two as will like use to find the data member we are trying to update. And let's further go into this get and int method to see what happened here. So you see this get and add method is where the mechanism will happen that we use volatile plus CAS to keep the thread safe. So here we are using the get int volatile method. Actually, this is just a method to read the expected value. So you see the v is the expected value. And after that, we will use the compare and set method. You see, the object contains data member we're trying to update, and offset, you see, the second value is the second parameter. You remember that we passed in is the offset, right? And combining with the object with the offset, we can specify which data member we're trying to update, and this v here is the expected value we read. And other thing is the same. Like we only update this v to v plus 1. Like remember the delta we passed in is 1, right? So we will only update it when the current value is expected is equals to this expected value. And if you see this is a do while loop, so this means if the compare set will return a Boolean value that indicates whether the compare set is successful or not. So if it is failed, it will using the do while loop to try again. read the new value, read the new expected value, and try to compare and set again. So you see, with this implementation, compare and set will be better. We can also call it an optimistic lock. So this compare and set, you better use it when you do not have a lot of updates. So suppose you have many threads, they are keep updating your target value, then better just use the synchronize, because you see the implementation is using the do while loop, right? Most of the optimistic lock will use this do while loop implementation. So if you have a lot of write operation, then that means there is a high possibility that every time you are trying to update it, it not equals to the expected value, right? Because after you read it, someone just updated and you failed. So you will make your CPU keep running, like doing this do while loop, keep uh, wasting the CPU resources, but doing nothing but just running the while loop. So, but if you only have a, like, your program only have a limited write operation, then you can use this CAS implementation. So why it's called optimistic lock? That is because you always be optimistic that suppose there is limited people or limited thread are updating your value. So you can just without using a lock, but just use this compare and set with volatile to update your value. Because when you use a lock, it will slow down your performance significantly, right? But if you're using the compare and set, it's just a single instruction with the volatile. The performance is better, but if you have a lot of update, if the compare and set failed, always failed, then it will waste your CPU resources by just doing the useless while loop, right? So we can try to write a program that's using this atomic library to updating a value. So here maybe let's just initialize the value with 0, and we can still create a void, maybe static void increment method. So this method will just called AI dot get an increment. So make it static as well. So here we can do something similar, like create two thread, keep updating it. Just similar logic. Let's just update it for 10,000 times. Uh, let's just call inquiry. Copy paste the logic. So here, if we run run T1, run T2, and let the main thread to wait for them. Get system out. I believe there is a get method to get the value, right? Okay. And also, you see this join method need to be, will throw a unchecked exception, so we have to handle it. We'll have to write a throw or try catch block to handle it. And you see, because we have already examined the eternal implementation for this atomic integer, right? There is no such things as synchronize. It just use the compare and set to update the eternal data member value. So we try to run it, you see, I think we will get 20,000. So everybody was comfortable with this part, like the compare and set, and like how to use volatile plus CAS to yeah, like when you use the synchronize, it's just like a lock. So you will just block, you will make your method or make your code block um to be critical. Like it will block all the other threads. So synchronize will just like you said, will lock the whole method. If the lock you mentioned is the meaning um like making this method to be only be accessible by that one specific one method who acquired the monitor. The monitor is like a lock. Uh, um, so if we are all good with this CAS part, we can introduce the next topic. Any questions related to the idea of this? So you can also, if no questions related to this idea, let me draw a conclusion. Like also, may you guys might heard a lot of like the optimistic lock, right? Optimistic lock. So this opt right? I kind of forgot how to spell it. Optimistic. Let me think. Optimistic. Yeah, optimistic. So this implementation is also we call it as a optimistic lock. So optimistic lock is not a real lock like a synchronized or reentrant lock that you add lock to your code block, but it is using the volatile plus CAS. So it's just like when you're trying to update your value, you just try to compare the expected value with the current value. If they are same, you update it. So this is called the optimistic lock. And something like in the database, how you implement this optimistic lock is like every you will keep a version with your every data records. Like when you're trying to update your data records, you will try to compare whether the version is still the version that you read previously. If it is not the same, then that means um, when you try to update it, before you update it, someone has already changed the value. So you will just read again and based on the new value to try to update. And also you still when you update, you have to check the version. So the idea is the same. Like when you try to update the value, you first check whether the current value is the same as the expected value. You only update it when they are the same. So to make sure that you always update the value based on the correct expected value, right? So this is also called an optimistic lock, but the optimistic lock is not really a lock. So the advantages of it, you see, we're using a while loop to keep trying to update it, right? So better better to use when there is not much updating, right? So this is how we use. So if you have a lot of updating, you better just use the synchronize to avoid like wasting your CPU usage. And yep, I think this is all I want to talk about the CAS. And if no questions related to this, let me briefly introduce something called blocking queue. So we will introduce this blocking queue because the thread pool that we are going to introduce is using this blocking queue to store it tasks. So like when you have, you see yesterday we learned how to create a thread, right? And also the thread is just like a one-time thread. When you execute the task, then your thread just gone. But creating a thread is kind of expensive. So we will trying to save the system resources by using the thread pool that we will reuse the thread. After we finish the task, we just return the thread to the thread pool, but not just terminate it. So, but you see, for the thread pool, it got some worker thread to work on the task, right? And also we also need a queue to like buffer the task, and then our worker thread can just pull the task from the blocking queue, right? So what is the blocking queue? So blocking queue is like a queue with some size, like for example, if we have a blocking queue with a size of 16, then that means we will have a producer and consumer for the blocking queue, right? And the producer will be like just a thread to constantly add elements into the queue. And consumer is something that will constantly pull elements from the queue. So the blocking queue is something like when the queue is full, like the queue is size of 16. When the queue is full, then it will block your producer to say, hey, I'm full, please wait. And then the producer will wait there, got blocked. And only when the queue has like empty slot, then the producer can start to produce elements again. But for the consumer, it's kind of same idea. That's when it's trying to pull from the queue, it finds that queue is already empty, then it will be notified that please wait until there is some elements being added into the queue. The queue is not empty, then you can start to pull the element from the queue. So we can give a demo blocking queue like my BQ. So here, like just we just for illustration, maybe we just create an integer queue. So here we have a queue, right? And also what we need is like a capacity. So this just the maximum element that we can hold in our queue. Maybe let's just and let me also create a constructor. So this constructor will take a integer number that is the capacity, right? And let me, here we will use this input to define the capacity and also like initialize a queue. So for this demo blocking queue, let's just implement two methods that for the usage of the producer and consumer. So producer will need a add method to add element into our queue, right? So we have to provide a maybe a void. Let's call it put or add. Maybe offer. I think offer is better. So offer an integer element. And what we're trying to do is when we first like trying to put the element into our queue, we want to first check whether the queue size has already arrived the capacity. So use a for loop, use a while loop to check it. So if we just if we use the if statement to check it, maybe it would not be sufficient because if just a one time checking, we want to keep checking whether when the producer trying to use our off or method, we want it to keep checking whether queue is full or not. So here, let's like just if the queue size is greater or equal than the capacity, then that means we have to like wait here until the queue size um, is less than the capacity. Then that means we can start offering our element, right? We can just queue the offer the element, and this is like the method for the offer. So it um, satisfy the idea we mentioned previously, right? When the queue size exceeds the capacity, we will block the producer, and only when there is empty slot, we start to offer the element. And also we will have a maybe call it pull method. We will pull the element from the queue, and also we will have the similar idea that when the queue size is like less or equal than 0, then we will just like let our consumer to wait here until the queue size greater than 0. Then we can start to uh, pull the element out from the queue. So this is the like very simple demo for the blocking queue. But this implementation is not thread safe, right? So see, if two if two producer, like two thread, they are producer, they are trying to invoke the offer method, but because we do not provide any thread safe in uh, we do not provide any thread safe like properties, then if the two threads, they both, suppose now the queue size is 15, and this two thread will both find that the queue size is less than the capacity 16. So suppose we now have a capacity of 16. So they both find 15 less than 16. Then they will both try to offer the element into the queue. So in this case, it will exceed the size of our capacity, right? And it will causing some error. So in here, because we are just using a linked list, so it allows you to both add into the queue. But suppose we have an array, then it might give you like if you just have a real capacity, like there's only 16 slots, then it will give you some error, right? Even here, this is not allowed, like because where capacity is designed to be 16, if you have 17 elements, it's not allowed. So it's not a thread safe implementation, right? So in this case, can we use something to make sure that our blocking queue to be thread safe? Any idea, like to modify this version to be a thread safe version? So now you see there is a possibility that two threads are trying to update to trying to offer an element into our blocking queue at the same time. So is there any way that we can resolve this to make it thread safe? Mm, any idea? So like for example, if we the problem the let me think. The reason that causing this problem is that we are letting two threads to at the same time to offering an element into our queue, right? So is there any way that we can make sure that every time only one thread can enter this method, or at the same time only one thread can um, can start offering element into the queue? Mm, yeah, correct. We can use synchronize, right? So by using the synchronize, uh, we can make sure that at the same time, only one thread can entering this method, and then it will be all right that, um, for example, if I have a method, you have a thread one called producer, sorry, producer, and it just calling the, like, maybe call it producer one, and trying to, oh, first we need to have a blocking queue instance. So let's create a myBQ instance. And oh, we will need the capacity, maybe just be 16. And here, let's just like calling the offer by one. So if we still have another producer trying to produce element into it, maybe for better illustration, maybe we have to use something like a for loop to like keep adding element into it. Then there will be like a conflict between those two, right? So, but for illustration, let's just keep it simple. So you see, we have two producer trying to offer element into the myBQ, right? The myBQ instance. And if we make the offer to be synchronized, then we can make sure that at the same time, only one producer can offering elements into the queue. Is there any way to let multiple thread to work at the same time and at the meantime make it thread safe? That is a good question. So if we allow multiple threads to work on this queue, I think there is one implementation will be similar to the um, concurrent hash map. So in this case, if we want to do that, we better to like adding lock on each bucket, not the whole table. Like suppose we have a like a blocking queue, right? And for now, whenever we're trying to add elements into our queue, we just block the whole queue, right? So in order to make it thread safe. But in order to make, like, I do not have the implementations for now, but I think if we can achieve something just like the concurrent hash map, we synchronize on each block, each entry, then I think it is thread safe to allow all the threads to work on your queue simultaneously, but working on different buckets. So if they are working on the same bucket, it's still you should naturally blocking them, right? Because you cannot just let two producer to produce element at the same time to one bucket, right? This is absolutely not thread safe. So maybe you can do something like just locking the bucket that you are trying to update. Maybe you can create instead of just using this queue, you using something just like the um, hash map or concurrent hash map, you using a node array, right? You have you create a class of node and uh, doing something like write some logic there, and now you have the node and you have a node array, and you create a node array to maintain all the task or elements. Uh, and in this case, you synchronize on, like when you're trying to update the value, you just synchronize on each node rather than the whole table. I think it's also thread safe. So it's like But I think if I try to implement here, what I will do, like both of them find the queue less than the capacity, then trying to update, but we just synchronize. Maybe if for this implementation, maybe we can just synchronize the each node. So yeah, I think that will be a tricky implementation. Yeah, but the idea, I think we can do something like that. I'm thinking if I can come up with the idea for how to implement that. So oh, but it will be kind of we will need some helper function to like find the empty slot and then trying to update on the slot. Yeah, I think that will need a lot effort work. Maybe we do not have time to like spend a lot of time on how to design those. But I think the idea can be that. You should check specific index using node array, using a queue. We can only exact element from my end. Yeah, because this is called like a blocking queue. So your element should oh yeah, this is a queue. So we only need to check the first entry, right? Because it's the first in, first out, right? Right. You're correct. So the reason we are using a queue, that is because later we will use it, like the thread pool, we use it, and we want our task to have a priority, like the first in task will be first served. So here maybe we can have like as you said, we can have an index to keep track of the current index to add like this. And also maybe we have to keep an index to pull like this. And every time when we try to offer an element, we will increment this index. And also every time when we try to pull it up, sorry, before we pull it, we will, but this will like we will have further check, like take the module, but I think it will be a little bit tedious. Like you have to take the module of 16, but not the capacity. The index to like take the module. Oh, sorry. Just capacity. Yeah, maybe you have to do something like this. And also for the pull, every time you pull an element, you have to also make the index to pull to just like the similar logic. But this will make your queue like to be a circular queue. So you're trying to, and every time when you're trying to offer an element, you have to, but I think still not sufficient, right? So if you allow two threads to concurrently working on your queue, just with this index to track which is the bucket that you need to operate on next, is still not sufficient. Like we have to have a mechanism, like if this is the next empty slot, we have to make sure that one thread is adding on this one and another thread is working on this one. But another reason I think, yeah, I think if we want to achieve this, maybe it will need a lot of extra work. Just Yeah, maybe for today, let's just keep it simple. Yeah. But I think we can do that with some idea like that. But here, let's just keep it to be simple. And oh, so here we just when we're trying to update it, we just synchronize the whole table. So, but with the so we just synchronized. One thing is that for now we are like keep our producer to wait in the while loop, right? So remember yesterday I introduced one thing called wait, right? So we cannot we can just when it is not when the queue is full, we can just let our thread to wait, uh, like called this wait. So but it will ask us to throw some unchecked exception. Maybe we should wrap this whole thing in a try catch block, but here maybe let's just wrap this, only write the wait statement in the try catch block. So so here we just whenever a producer tried to find the queue is full, we are letting it to like release the block of it, release the lock of it. So in this case, other thread can get the lock and work on our queue, right? And so also we need to, after we let our producer to wait, it make it to in the wait list. So we have to also need to invoke it, like to make it work again. So when do we want to invoke it? That is when there is empty slot, right? So we will, whenever a queue got pulled out, but I think maybe if I just write something like this, like mm, uh, let me think, should be signal all, but I haven't touched this for a while. I'm not sure whether we can directly call the signal. Let me think how to signal all. I forgot the syntax. Let me give me a second to check it. So all right, still not signal, it's notify. So here, maybe I want to notify. Yeah. This notify all method is used to like invoke all the threads that are waiting for this lock. So previously we set our producer to wait in line, to wait for there is empty slot for it to produce its element. So here we will use this to notify. But I think this is not a good sequence, right? You see, if we notify it before we pull it out, then there is a risk that our producer wake up and find that the queue is still not do not have an empty slot. So maybe we um, better change our implementation, like something like this. We will pull first, and let just maybe have an int value called results, then return the results. This will make more sense. Like after we're pulling the element from the queue, then that means there will be empty slot in the queue, and then we can start to notify all the waiting threads to wake up to try to produce or try to pull. So also the similar thing we have to make, the similar changes we have to make is in the consumer method, right? We still like copy paste this. We do not want it to keep doing the while loop because it will waste our CPU usage. We just make it wait. And when after we offering an element, we will notify our waiting consumer to start to consume it. So let's say notify all. And this will be our thread safe implementation of the blocking queue. But you see, there is still one problem that we cannot resolve by using the synchronize, right? You see, when you're using the synchronize, you let your current thread, so this this statement will make the current thread that running on this method to go to sleep, not go to sleep, like to go to wait stage. So, but you see, if we have both producer thread and consumer thread are like waiting, when we call the notify, either from like this pull method or from this offer method, we will invoke all the waiting thread that we cannot specify that when I call the notify all, actually here, we only want to, we only want to invoke the consumer, right? Because when we offering an element, we are not, let's say, hey, please, another producer, wake up, please produce. We only want to invoke the consumer that let the consumer to consume our newly added element. But we also, same here, when we pull an element, we only want to inform the consumer that, hey, I have already consumed one element. Maybe there is a slot that you can start offering element. But with the synchronize, we cannot do that. We only have the like notify or notify all. So the difference between notify and notify all is that notify only wake one waiting thread, but notify all will wake up all the waiting thread. So but both of them cannot specify in that which type of thread we want to wake up, because the synchronize only provide one waiting list. So all the producer or consumer, they just waiting in the same waiting list. So we cannot specify which consumer or producer we were trying to wake up. So this is one of the disadvantage for synchronize. And also another disadvantage is that the synchronize is not a fair lock. You see, suppose you will have many thread waiting for offering elements, but they will have a sequence. Like maybe thread one came first, and then thread two came second, and they have an order of their entering time, right? Like thread two, or maybe call it producer one, producer two. They have a order of their arriving. But with the synchronize, when you're trying to notify the threads in the waiting list, they just compete together. It's not fair. Like they're not waiting in line that say, hey, I'm first come, so I should first, when you notify all the thread, I should first compete for the monitor. It's not the case. Synchronize does not provide a fair lock. It just let all the waiting threads, like maybe some consumer even in the waiting list, because there is only one waiting list there. So all of those threads will wake up and try to compute for the lock, try to compute for the monitor. And if they are success, they will resume running from here and try to test the condition again. If it's satisfied, we'll start offering. So all of them will wake up and competing at the same time. There is no fair lock. So this will be the two disadvantages for using the synchronize to achieve your thread safe blocking queue. So let me write it down. So this advantages blocking queue. Oh no, synchronize. Sorry. So one is that we mentioned that there is only one waiting list, right? We cannot specify which waiting list to wake up. So we just wake up all the threads in one waiting list, that all the producer consumer wait in one waiting list. So one disadvantage is only one waiting list. And also another is no fair lock. Like even though producer one came in first, but when you notify, they just let all the threads to start competing for the monitor, and there's no fair lock. So these are two of the disadvantages for synchronize. And also for synchronize is like there is no try lock. You see, if you are using synchronize, there is no try lock. You just what you do is when you get blocked, you just keep blocking there, and until you are you are able to uh, get the lock or something like that, you just keep blocking outside there. So, but there is one thing called try lock, is that thread one came here and find that the monitor has already been acquired by other thread. Then it said, hey, I just give up. I just doing other things. This is like a try lock. It's not keep waiting there. But synchronize is like when I try to call thread the offering, but they found the monitor has already been acquired by other threads, then it will keep waiting there until it get the monitor and entering. It's not the try. There is no try lock for synchronize. So those are the disadvantages for synchronize. And later, I will introduce something called reentry lock. So that is a lock that has multiple waiting lists, and also it will provide you an option to implement a fair lock, and also it provides you a try lock. So, but for now, let's just take 10 minutes break, and let's resume at 11:25. And if you have any question, let's just discuss it during the break. So if one thread caused wait while getting into the synchronized method, will there be a deadlock? So I think it won't cause a deadlock. So you see the deadlock's definition that I will introduce later, like it's like a thread one is holding like thread one holding lock one, and it's trying to try to acquire lock two, right? But thread two like is actually holding the lock two, but it's trying to get lock one. So this will cause a deadlock, that the thread one is keep waiting for the lock one, and the thread two is keep waiting for the sorry, I messed up. Like the thread one is keep waiting for the lock two, because the lock two is actually holding by the thread two, and but thread two is actually trying keep waiting for the lock one, but actually lock one is already held by the thread two. So these two threads will block each other. This is called the deadlock. But the wait means, remember, is that I mentioned previously, the wait will release the lock, right? So if you release the lock, then that means you will not block other threads, right? In this case, maybe you thread one, just release the lock one, then the thread two can successfully get the lock one and then execute all its logic. So there will be not a deadlock. But I assume that what you are trying to say is that I let it wait, and no one notify it, no one wake up it, and then it forever wait there, then if you poorly design your blocking queue, then there is a possibility for that, like the forever wait. So you see, if I just use notify, then maybe or like if I just use the notify, then that means only one thread maybe wake up. And unfortunately, I wake up the maybe like unfortunately I wake up the wrong thread. Like I supposed to wake up the producer, but I wake up the consumer again. Then the producer not get invoked, and I only notified one thread, and the consumer another consumer wake up and find that the queue is empty, and then it also goes to wait. And but your producer never got wake up, then there is a possibility that your producer just like forever waiting there. So there is a chance that if you poorly design your notify or something like that, your thread have a possibility to wait forever there. But it's not due to the deadlock. It's just because no one wake up it.
Okay, I see. So the synchronized will automatically create a log for the method. Do I understand it correctly?
So the lock you mentioned, I suppose, is the monitor you're trying to say. So
Uh,
like the monitor, like I explained yesterday, the synchronize should work with a monitor, right? So how it achieve this critical part is to the monitor is just like a log. So if you are using a log, is something like you will call something like log, right?
yeah.
And then you can log your code block. But something is similar is that when you're trying to enter this method, you're trying to acquire the monitor. So this step is just like you are calling the log, right? You're trying to get the log. At here, you're trying to get the monitor. Only when you
Okay.
successfully get the monitor, you can execute your code block.
And all the methods declared with synchronized, they are all using the same monitor, right? Like the
Uh,
offer and the pull here, they are using the same monitor, so they are synchronized.
so there is a possibility that they are trying the different monitor. So as I explained yesterday, remember that when I synchronize the non-static block, actually they are trying to acquire the monitor of the specific instance. So you see here, the instance is the BQ instance that are created. So when you're trying to call the offer or trying to call the pull, it will trying to acquire the monitor of this object. But suppose you have two blocking
Uh,
queue.
yeah. So we assume that we are referring the same object.
Mhm.
Then the monitor should be same.
Right.
Okay.
There should, yeah, that's correct. Yeah.
And what if we just declare a log, like we just created a log on our own, then we'll wait, release the log when yeah, we'll wait release log. So for example, if you just created a log
Mhm.
inside in the beginning of offer method, instead of calling, instead of using synchronized, then we'll wait, detect the log and release it when the wait is invoked.
Yeah, I think you're supposed to release your lock at this point, because if you do not release your lock, then you will block the other thread trying to execute the code, right?
And how about in a situation that you created two logs, and then like will wait release all both the logs, or it will depend.
You mean two lock is like you
Yeah,
lock one, the
and
lock
log
and
two.
lock two. Yeah, I think if you are doing this due to some maybe security reason, I think in here you have to both release the two lock and but Like I think if you have your own lock, yeah, you have to release it at here. And also when you finish your logic, you should release both of the lock in order to let other thread to successfully executing the logic.
Okay.
So the reason we use lock is just to make the code block to be critical, right? Otherwise, there's a risk that multiple threads are working on it simultaneously.
Okay. And so when should we create a lock explicitly instead of using synchronize?
Like the most commonly seen lock implementation is reentrant lock. So I will introduce it later. So like I said previously, the disadvantages for the synchronize. You have those, like you only have one waiting list, so you cannot specify that which waiting list you want to wake up the threads waiting in it. And also you do not have a fair lock that all the thread waiting in the waiting list just be wake up and compute together. They do not have a like a first in first serve order. And also there's no try lock. So if you want those features, you better not use the synchronize. You want to use something called reentrant lock. So the reentrant lock will provide you all those features like test lock. Oh, sorry. Maybe let's just create a reentrant lock. You see, the reentrant lock, it provides you when you construct it, it provides you a Boolean flag to set whether it is a fair lock or not. If it is, then it will, if it is a fair lock, then it will use the ordering policy to like will let the first wait thread to be first wake up. And also it should provide you a try lock.
Oh, so by using synchronized, all the threads are going to be picked randomly instead of first in first serve. So
Right.
okay, that makes them unfair.
Yeah,
Okay.
it's unfair. So you see, also there is a try lock. So the try lock will only try to acquire the lock once, and if it failed, just to return false, but not like here. We just block there and keep waiting until the monitor is free. So we can use try lock. So like something like what happened here is like we use a maybe a log.try log. And then if it is failed, we can use something like if it failed, we just like return or something like that. So we will not, but this is like remove this synchronize, and you can enter there and you find that the lock is already being acquired by other thread. You know the lock is not available, then you just return. You're not waiting there. So this is a
Okay.
try lock. Yeah.
Thank you so much.
Okay, no problem.